So this is lecture number 18, EE211, analog circuit design. Right. So previously we talked about many different things. One of them is like single stage amplifier, current mirror, frequency response, and we have started with differential amplifier. In differential amplifier we have learned so many things, like when we are saying the differential signal, it's all about there are two inputs, there might be two outputs, or but if there are two inputs, two outputs, it's known as fully differential, and all are 180-degree phase shifted with each other. This is the thing which we are doing to achieve only one thing, and that's removing second order or even harmonics. Second part is we also want to remove common mode noise. Generally this common mode is DC value, and where DC is not purely DC but there are some fluctuations on top of the pure DC. So you want to remove that, and that's what you are doing. And we discussed some of the advantage over that, and we also talked about one fact that if there is a single-ended circuit, if you want to make it differential, you have to exactly make identical copy. This control C and control V has to be here, like it's identical copy. There is no difference between these two boxes. They have to have been connected with VDD and ground. But while connecting the inputs, both have differential input with some common mode voltage. This might be DC, it might be some other thing also. You can see here, and this is what giving us an advantage in terms of even harmonics, and also like we are also getting advantage to remove the common mode noise which is happening at the DC or the common mode value. So it can be removed, and we are taking two outputs. So we talked about this. We also learned that this kind of circuit which does not have any connection, then it's called pseudo differential. Whereas in the case of the fully differential or differential, where there are two outputs and two inputs, they are linked with some wires in between. There must be some connection other than output. There might be some wires connected, or they are actually dependent on each other. So that is what we need to learn and we need to understand. But before doing that, we also understand that if such two circuits are there identical to each other, if they are connected with some wire, and if this side I am connecting plus V in, let's call it plus V in, and other side minus V in, this particular potential is going to be zero, and which we are going to call it virtual AC ground. Other than that, we also learn that, but by the way, this virtual AC ground only happens when this is V in and this is minus V in. But in the case when both the circuits are linked with a wire, and both side I'm giving equal value of voltage. Let's call it V in. Then if I'm connecting here a resistor, the current flowing through this one will be 2I if this is I and this is I. And this potential is depending on the resistance and other things, right? Current and resistance. So we studied that. Now let's start with the theory known as pseudo differential amplifier, where there are two transistors M1 and M2, and RD is the load resistance. Now I need to find out the gain. If I need to find out the gain, what I can do, I can simply write down. By the way, this is pseudo differential by making the fact that M1 is exactly equal to M2 and RD is 1 equal to RD2. Right, that is what actually differential is. And V in 1 and V in 2, we are giving the differential signal with some common mode value. So you can see here it's already given. Now if I want to find out the gain, let's start with like both the circuits are independent, they don't talk to each other, or one circuit is not giving any effect on another circuit. In that case, you can write down V out 1 is equal to, it's a common source amplifier and we know that it's GM1 times RD1 in shunt with RO1 times V in 1, that's V out 1, and V out 2 is nothing but minus GM1 times RD, sorry, it has to be GM2 RD2 in shunt with RO2 times V in 2. If I am interested in finding out the differential gain, it's V out 1 minus V out 2. That becomes, let's assume that GM1 and GM2, like assumption is saying that GM1 equal to GM2 equal to GM and RD1 equal to RD2 equal to RD. In that case, this becomes GM minus GM RD, and of course RO1 in is equal to RO2 equal to RO. Times V in 1 minus V in 2, right? So if you are talking about the differential gain, which is actually V out 1 minus V out 2 divided by V in 1 minus V in 2, that remains minus GM times RD in shunt with RO, which is similar to what we were seeing. However, you can see that the input is getting doubled because of this V in 1 minus V in 2. So if you take the difference of these two, it will become, so differentially, okay, I need to draw not here, but it will go to 0, something like this, because this common mode goes to 0 and this difference becomes twice, because both of them are 180-degree phase shifted and of course having equal and opposite sign of magnitude, right? So that is what you are going to see here, and there are two outputs you can draw individually. Both will have some output common mode voltage also, which you can call it VOCM. Here V in CM was the input common mode voltage, which was biasing both the transistors, whereas output common mode voltage is because of the fact that there is some some drop over here. On top of that, this is acting as a, like, voltage is actually riding on this one, right, which is output common mode voltage. So that is what drawn here. We found out the gain also, no problem, right? But there is some specific limitation because of the input and output common mode value. So if you understand the thing, So if we are looking at only and only one part of the circuit, single-ended, which has VCMI and there is V in. So with respect to time and voltage amplitude, if I am feeding this kind of signal where this is VCMI and input is like this, role of this particular DC line is to make sure that this transistor is in saturation. However, if you know the output common mode voltage VCMO, which is actually VDS set, is actually higher than VCMI. This is already known to us. Otherwise, this doesn't work, right? VCMO has to be higher than this one so that this transistor goes into saturation and it's beyond the VDS set line. So if this is the case, and we know that some part of the value, and this is VCMO over here. Note that VCMO is always higher than VCMI, and I'm keeping one more 9, which is, let's draw it with green color. Let's call it VDD, and let's call this one as 0. These two green lines indicates that my output cannot go beyond VDD or below 0. That's the energy conservation law, and that's the always like the property of any circuit, right? So now if this is going up, you can see that when it's getting amplified, if it is getting amplified, it may look like this, but as we know that it cannot go beyond this value, it has to restrict the output here, or we can draw the hash line which indicates the output. Now there are two possibilities. Either I can reduce this VCMI, but in that case maybe like this transistor goes into linear mode or in cutoff region. I don't want that. I want to use this one as amplification or the amplifier. One of the possible thing is, rather than making it large signal, let's make it a small, really small value which is playing the role over here, and it's depending on VCMI. So I decrease the input amplitude so that I can see the output which is actually not reaching VDD. I can do that. There is no problem. So things are here actually controlled by VCMI in terms of getting saturation or getting clipped off, and always VCMO is higher than VCMI, right? In the case of PMOS, it will be different, where you will see the saturation at ground side. So you must have experienced same thing when you have done the experiment on common emitter amplifier, where there is some resistive load and your output reaching here. Most of the time it's positive side, and it's creating lots of problem to you. So in that case you reduced the input amplitude just to find out the exact value of gain, right? Because it become large signal. You should not give the large signal value uh, of the input signal. So here the main culprit is the input common mode voltage. If input common mode voltage and output common mode voltage are at same place, then there is no problem. If the output looks like this one, no problem. Or you can say that if VCMI is equal to VCMO is equal to exactly VDD by 2, then I can get better output swing. But that's not possible. So if you appreciate and if you understand, there is a problem that there is a saturation at the output, and that leads to have the distortion. When we are saying the distortion means you're going to have harmonics, right? So harmonics are coming because of the fact that the the shape of the signal. For that, you must have studied something called Fourier series, Fourier. So you can find out for such system when it's saturated on top side, maybe saturated on bottom side, saturated on both side, then what is happening and how the harmonic distortion, the first fundamental, with respect to fundamental, what are the other frequency components coming into picture. But as you are taking the difference of these two, definitely you are not going to have following frequencies: 0 hertz frequency, which is DC, and even order harmonics will not be there. Still it will not be there because that's the property of the differential signal. When differential you are taking means V out 1 minus V out 2. So you can find out, and you can, through this shape, you must have studied in your other courses, like for this shape, how much is like different harmonics, right? First, second, third. So it will definitely introduce some harmonics, and the amplitude of the harmonics are higher. So you need to see all these things, and you need to make sure that those things should not occur in your circuit. And that's how, like, it was an invention of pseudo differential to differential circuit. So this is the problem with all pseudo differential circuits. It's not the case for other circuits, but as you can see, pseudo differential is not is a combination of two single-ended circuits. So this is V out plus, let's call it V out minus, then this is V out plus, and this is, so we already studied this. We know that both are independent. When we are clubbing them together, then you can see that it gives the advantage as a differential circuit, because we are taking the difference of inputs, difference of outputs. And when we are saying the differential, it's 180-degree phase shifted, and that is going to give you two major advantage. One is the common mode noise removal and the even harmonic removal. However, because of the bad value of V in Cm, you might land up with the harmonic distortion because of getting saturation. So this particular circuit, or the pseudo differential circuit, has a major disadvantage, that it's sensitive to common mode voltage, right? However, as it is differential, it has two advantages: that common mode noise is removed, and even harmonics are removed. So we are worried about this part, because the output is not having the proper swing, not having or the distortions are observed. We don't like that. We want to have better and better signal to noise ratio. We want better to better total harmonic distortion. So in the case of different circuits in power electronics machines, or in the case of like communication circuits, or the case of data converters, you need to take care of such quantities so that you can achieve the required number of resolution or the required specifications from that particular circuit. So in that case, what I'm saying, the solution of pseudo differential is the differential or maybe fully differential. Differential is the one where two inputs but one output, whereas in the case of fully differential, which is more advantageous to us in terms of not only giving a differential input which is 180 degree phase shifted, but we are taking the output which are also 180 degree phase shifted, where even harmonics are reduced and the common mode noise is also zero. So what I'm saying, instead of having the circuit which was like this, where both side everything is same, we did this. We already did this and we learn it. But here the problem was, as this is pseudo differential, it's sensitive to the common mode voltage. So what my point is, let's connect this one to some current sink value. In the case of PMOS, we can have current source also. So if you have this one, this current is depending on two branches because it has to follow KCL. And the outputs are taken from here. If this is V in plus and this is V in minus, if these two are V in plus and V in minus, relatively this will be V out minus and V out plus. As this is 180 degree phase shift between input and output because of the common source amplifier, I made the opposite sign. You can see that, right? And of course there will be some load resistance or load capacitance I am not taking into account right now, but you can see I'm adding one extra current. It's very elegant design which gives you advantage over pseudo differential. However, this kind of circuit has connection between these two circuits. So this is balanced network number 1 and this is balanced network number 2. Both are linked with a wire and I'm connecting to some current. You can connect with some resistance as I explained you earlier. What is going to happen over here is we are going to study. So here you can see that output common mode voltage is fixed to with ISS. If you look at this one, and let's call this one as ISS as named in Behzad-Razavi, output common voltage is depending on not only now input common mode voltage, but no matter what input common mode voltage you are giving over here, VCMI, the output common mode voltage is depending on the current flowing through the branches and the GM offered by M1, right? So this is very important. If I am giving VCMI both side same, which is sufficient enough to make these transistors in saturation, now output common mode voltage does not depend on VCMI. However, it depends on current flowing through the circuit and GM and the resistance offered in different nodes. So that is going to give me the output common mode voltage. So VCMO is not a function of VCMI anymore, which was the case for pseudo differential amplifier. So that is what I wrote it here, that output common mode voltage is fixed and decided by ISS. Transconductance of the amplifier varies because of the input common mode voltage. That's the one fact. And because of transconductance and ISS, you may have different VCMO. However, it's not directly proportional to that because GM is getting saturated after some value of VCMI. Moreover, input common mode voltage does not determine the output current flowing through input transistors M1 and M2. Like the case of our pseudo differential, where as I am increasing VCMI, the current flowing through this one is going to increase, and it's like this output current also depends on the input common mode voltage, which is also one of the problem, and we need to fix that. So in this case, as I am fixing this current to ISS, no matter what VCMI is going up and down, it determines GM. However, the current flowing to these two branches has to be governed by ISS, as this is following the case here. So if both side, if I'm giving exactly equal uh, value of input common mode voltage, you can see that, and when V in both side V in are 0, then the current flowing through both the branches are equal, or you can say that they will be ISS by 2. This is a very very elegant one, because it's it's following the case here. It's not creating any problem anymore because of VCMI. So VCMI's role is to fix the transconductances, and once those are fixed, there is no problem. So input common mode voltage does not determine the current flowing through input transistors M1 and M2. ISS determines the output common mode voltage, however. That is the fact, because we fixed it because of ISS. So here there might be like, you can use some sort of current mirrors and you can design it, or you can keep even some resistance. Notably, this part of the circuit and this part of the circuits are exactly identical, or you can say that RD1 is equal to RD2 is equal to RD, and M1 equal to M2 equal to M, or you can say that GM1 equal to GM2 equal to GM, RO1 equal to RO2 equal to RO whatever, right? So all are identical, and you can say that in this case everything is matched as we want. The circuits are matched, having equal multipliers, equal fingers. Whatever you are doing with M1, it's same at M2. It's just control C and control V. It's very simple, right? And this is what we are doing because of one fact. We want every slope in the equation of y equal to mx plus c, m has to be same, where m is acting as gain over here. And for non-linear circuit, you might have different gains for different frequency. Like at fundamental, you want m for the left hand side circuit same as right hand side, and same for all other harmonics gain also. So if this is the fact, then you can have all even harmonics to 0 and common mode voltage to 0, right? So this is what the advantage part. Now let's look at this circuit one more time. What is happening over here? If you remember, if there are two identical circuits or the two balanced block, if they are connected with a wire, and if I am applying here one side V in 1 and one side V in 2, and if V in 1 equal to V in 1 equal to minus V in 2, it means that I am giving differential signal. If I am giving differential signal, the Vx is become 0. However, this is happening only in the case of the differential signal, which is AC by nature. We are going to call this one as virtual AC ground. But note that this is only happening in the case when both sides I am applying the differential signal. When I'm saying differential, v in 1 equal to minus v in 2, and that gives us lots of impact. Or we can say that Vx becomes 0 or virtual ground even though I'm connecting any circuit over here. It does not make any impact on that, right? And Vx is equal to 0, so the current is not going there, but it's going either of the direction, right? The direction is 1, so virtually Vx is 0. So this is what we already learned and we understood through the basic analysis in terms of balanced network. Also, we understand that if you look at this Vx node is acting like a seesaw when there is differential signal, so equal and opposite weight. In that case, this potential always remain at the same place, means 0. We call it AC virtual ground. Some people also make this analogy as like not calling this way, but they are saying that it's a weighing machine. The weighing machine, this is the ancient one analog which you have seen with some of the local vendors. So this point always remains Vx and it's AC virtual ground. However, if you look at this, the current flowing through each of the branch is also depending on the input common mode voltage, because there are two different terminology over here. When we are going to give the DC potential, let's talk about maybe this circuit. When we are going to give the DC potential over here, VCMI, both the circuits, the current flowing through these two branches are fixed, ISS by 2, ISS by 2. But because of these small signal on top of the common mode, the current is getting fluctuating, and this AC analysis, this potential becomes 0. When this is differential or when they are equal and opposite, then this becomes 0 AC virtual ground. That's why I'm insisting on adding the word called AC over here, right? So this is one thing which we already took care. But as I told you, like there is an analogy coming with this weighing machine, and the middle point is always 0. However, this VCMI is actually acting as a spring in between this one. This is in my hand, by the way. I am holding this. So you can see this virtual ground is virtual ground. It's always no matter what spring is there. However, because of this weight, this common mode or this value of the DC is going to change. This is VCMI, which I have fixed its stiffness and other things, and because of that VCMO, which is always higher than VCMI, this spring get elongated on the basis of the weight which you are keeping over here, and because of that weight, sometimes like it gets saturated also, it can reach VDD. If you are feeding here very high value of sine wave, means higher weight, this spring will get elongated and it will reach VDD. Whereas if you are feeding the small value, this is going not be like so much elongated and it's not going to get saturated, means it will not be damaged, right? When it's damaged, it's reached saturation, it reached VDD or ground, and that's what happening in our circuit. Here the output common mode voltage is actually decided by two part. One is called current and one is also input common mode voltage, but its impact is very low. The current flowing through these two branch are only depending on this one, and it's depending on the one fact that what is the input common mode voltage you are giving there. Sometimes even if it's going in cutoff, still this whole phenomena will work. What I mean to say is that if by some chance if this is ISS, let's only talk about the common mode voltage analysis. So if both side sorry, not common mode, differential one, if this side I am applying 0 and this side I am applying VDD, by the way this is VDD, this is V out 1 and V out 2. So notably when I'm applying 0 over here, this is going off and V out 1 becomes the current flowing through this one, ID1 and ID2. This is RD, by the way, this is RD. V out 1 is nothing but VDD minus ID1 RD, where ID1 is 0, right? Because it's in cutoff. 0 volt available at this transistor means it's in cutoff. So V out 1 becomes VDD, whereas if I am applying here VDD, this is short circuit, right? This is short or allows the entire current to flow from here. So it's ID2 is flowing from here. In that case, V out 2, which is also VDD minus ID2 times RD, where ID depends on this equation ideally, where the gate to source potential is controlling. However, here you have to just decide whether the transistor is in saturation or in which particular mode of operation it is. You will find out the offered GM of this transistor or the offered capacitance, and this ID current won't work over here. This won't work. It's only decide to find out the current and to find out the GM. But here, once this is the done, then it's VDD minus ISS times RD. Notably, because it's KCL and entire current has to flow from somewhere, because if this particular guy is asking for current ISS, if this guy is not giving any current, this guy has to provide all the current. Or if I'm going this side, if this is VDD and if this is 0, then entire current has to come from here. If it is in between, then both the side current has to be equally divided. Or if you are going VDD by 2, little bit upside and little bit downside, both the side will be compensated accordingly, and some delta I current, which is actually small by nature, and this particular up and down, which is equal and opposite, which is known as here small signal AC signal, which I am giving on top of VDD by 2, then it's plus delta and minus delta I will be compensated with each other, and if you sum up these two, it's going to give me ISS, because that's the property of any circuit, because it has to follow KCL. It's a energy conservation law, right? So adding this particular analysis which I explain you, let's understand one thing, that if I am applying V in 1 minus V in 2 from 0, sorry, let's assume that this is not 0, but it's going from minus VSS to plus VDD. First of all, it's very easy to understand in case of V out 1. If V in 1 minus V in 2 both are 0 at the middle point, if both are 0 means both are equal. Notably, what I am doing here is DC analysis, it's okay, right? So in that case, both are DC values, and V in 1 minus V in 2, if both are equal, means it might be VDD by 2, VDD by 2, both side. If this is VDD by 2, if this is VDD by 2, as I told you, both side will have the equal current, and both current will be ISS by 2. No matter what other things you are keeping, RD, M1, M2, or other things like common mode voltage, the current flowing through both the branches will be ISS by 2, and the total current flowing through this node will be ISS, because we are giving exactly same voltage. But if I am giving one side 0 and other side VDD, what is going to happen? So if V in 1 is 0 and this is VDD, it's equivalent of, let's call this one as minus VDD rather than. So in that case, what is going to happen? V out 1 is going to go to VDD, as we already talked about this, because V out 1 is nothing but VDD minus IDRD. Right now current flowing through this one is 0, so V out 1 is VDD, whereas V out 2 is nothing but VDD minus ID2 times RD. Notably, RD1 equal to RD2 equal to RD, and M1 equal to M2. So GM1 equal to GM2 equal to GM, and RO1 equal to RO2 equal to RO. So in that case, the current flowing through this branch, if like other branch was 0, this branch has to be ISS. So this is VDD minus RD times ISS. Oh, sorry, I make mistake. So it's RD times ISS. But if you flip the situation, when this becomes 0 and this becomes VDD, the situation is here. When V out 1 becomes VDD minus ISS times RD, because all the current will flow from here, and other side it's VDD. In between also we knew that what is happening. This certain condition depends until the transistor is not becoming on. Particular transistor is not becoming on until that VDD is VDD and V out 2 is flowing all the current ISS. But the point when the transistor gets into the saturation mode, or going in linear and then saturation mode, it tries to share the current, and accordingly you will see this kind of image. So V out 1 and V out 2, if you are drawing with respect to VDD V in 1 minus V in 2, you are going to see such kind of analysis, and this is happening like in this particular thing. This happens when the transistor are in saturation, whereas here one of the like when it's getting VDD, the M1 was in cutoff. In this case, M2 was in cutoff, and notably these two are absolutely in saturation. But as this is increasing, you can see that it's going from saturation to cutoff side, and this one is going from cutoff to saturation. In between, of course, the linear will be there, and that's how you can see the curve, which is moving a little bit with some smooth curves. You can see it's not the transition going exactly the way, like it's not going like this, because of one fact that there is linear region, right? If you understand that, let's make one more thing, or we can conclude today's lecture in such a way that you can understand what is common mode and differential terms graphically. So for that, let's assume that I am applying here V in 1 and V in 2. By the way, V in 1 and V in 2 are combination of differential as well as common mode voltage. So if you are so much interested into that, what I can do, I can actually, rather than doing this, I can do, okay, I kept current also. So if this was V in 1 and V in 2, I'm saying I'm not going to do that. I'm going to keep two voltage sources in series, V in 1 divided by 2. Let's call this one with V in 1 divided by 2 and V in 1 divided by 2. Both are in phase. So V in 2 divided by 2, V in 2 divided by 2. So that works, right? There's no problem. On top of this, I can do one more thing. I can add in opposite direction so that effectively they are contributing 0. If this is the case, I can combine this, okay, sorry, this with this one, and this with this one. So notably, what it's going to give me, it's going to give me only two voltage sources. Let's make new branch which are going to have two voltage sources like this, whose values are like one is, both are plus by the way. Now in that case, this is V in 1 minus V in 2 divided by 2, and this one is V in 2 minus V in 1 divided by 2, and this one is V in 1 plus V in 2 divided by 2, and same over here, V in, okay, V in 1 plus V in 2 divided by 2. So if this is the case, you can just like, now we can remove this, and here you can redraw this, let's say with green, which has two terms, or let's make it minus and plus. This is become V in 1 plus V in, sorry, minus V in 2 divided by 2, and this side again it's same, V in 1 minus V in 2 divided by 2. I am doing this because of the fact that it's minus and this is plus, right? And both side it's commonly connect with a voltage called V in 1 plus V in 2 divided by 2. So in this case, you can see that the differential signal is differential. It's difference of two quantities, whereas the common mode is common to the entire network, and whose value is V in 1 plus V in 2 divided by 2. Whereas in this case, it's V in 1 minus V in 2 divided by 2. If both the quantities are same, let's say V in 1 and V in 2 are equal and opposite, then you can see it, this side it becomes V in, this side it becomes minus V in. If V in 1 equal to V in minus V in 2, right? Okay. So this is going to be treated as common mode input, and these two are treated as differential input. So any of the way you can connect it and you can find out. So now moving to any further thing, I believe this is good enough for today. maybe rest of the things we are going to study next time, right? And we are going to talk more on differential, like to find out the small signal AC gain, the common mode gain, and so many other things related to the differential amplifier. It also covers the common mode range, which is input side and output side. Yeah. So thank you very much for today.